So as we get into chapter 4, we begin looking at second order differential equations. And as an introduction, we look at the mass spring oscillator system. So a mass spring oscillator system is simply a system that has a mass in it, and then it's connected to a spring. And you know from experience that if you have a spring attached to something, sometimes it's at rest, but if we pull this object to one side and let it go, it's going to go back and forth. So it's going to oscillate left and right, left and right, left and right. Or if we have a hanging spring and we pull it and we let it go, that spring is going to oscillate up and down. And if we look at the behavior of that, for the horizontal spring, let's call this position x equals 0, and to the right, x is positive. Then if we were to make a graph of time versus the x position, then we would have a cosine or a sine wave. Now, if we didn't have any friction involved, let's suppose we had that sitting on some kind of roller or something, or that it was sitting on a frictionless surface, and if it was in a vacuum, then this would oscillate back and forth forever. We would maintain the same amplitude throughout its duration. But we know that in reality, we have friction involved, and it turns out that the force due to friction is that's a force that's fighting against motion, so that's a resistant or a negative force, and it's proportional to the velocity. The faster it's going, the more air is going to slow it down. The slower it's going, the less impact air is going to be pushing on it. Also, the spring, from Hooke's law, the force in the spring, that's a resistant force. If we pull it to the right, when we're stretched, it's going to be resisting and wanting to pull us back. If we push it to the left, the spring is going to work against us and push to the right. So that force is a negative force that's proportional to the stretch, and our stretch is in the horizontal direction. And then we could have some external forces. There might be times where we have some kind of motor or some kind of system attached that is oscillating, that's driving this system. It's pushing it back and forth, back and forth as well. So if we sum those forces, the sum of the forces is MA, and it's going to be in the x direction. So we have some external force that could be added to it. We have the spring stretch that's resisting. We have friction that's resisting. And then when we sum those, that equals mass times acceleration. Notice we have three different levels of derivatives and or integrals. We have position, velocity, and acceleration in this equation. So let's put these all at the same level. Let's put them all in terms of position. So we have one term that's in position. Velocity is the derivative of position, so x prime. Acceleration is the derivative of velocity, or the second derivative of position. So this turns out to be a second order differential equation. From analysis, or from just thinking about what happens with springs, that the solution to this is going to be of the form A sine omega t, where omega deals with the period, A deals with the amplitude, how intense that's going to be oscillating back and forth. And depending on what our external force is, it could be that we have two oscillations going on at the same time. If this is driven by an oscillating function, then it could be that we have a major and a minor oscillation going on over time. Also, one thing that happens if we involve friction, then over time this is going to be getting weaker and weaker and weaker. Each time it goes back and forth, since friction is going to be pulling energy out of the system, then our oscillations are going to get weaker and weaker and weaker. So over time, our amplitudes are going to be getting shorter and shorter and shorter. So it could be that we have an exponential decay involved in our system, as well as our oscillation. So that's just an introduction of we have lots of systems, lots of things that involve second order differential equations, and just a look at what some solutions look like. To some of these second order differential equations, we'll have trigonometric oscillations in our solution. Sometimes we're going to have some exponential pieces in our solution. So the first couple problems that they give us in homework, they get us to verify whether something is a solution or not. So, for example, they give us y equals sine of 6t plus 3 cosine of 6t. And then they give us the differential equation 3y double prime plus 108y equals 0. Y of 0 is 3, y prime of 0 is 6. And they want us, first of all, to verify that this is a solution of the differential equation. So how do we see if something is a solution of a given differential equation? Well, we take the various derivatives of it, we plug into our equation and see if it makes it a true statement. The derivative of sine 6t, that would be cosine 6t times the derivative of 6t. For the next term, 3 is a coefficient. The derivative of cosine is minus sine times the derivative of the inside. So our first derivative is 6 cosine 6t minus, let's see, 6 times 3, so 18 sine of 6t. And our second derivative will be, if we take the derivative of the first term, we have a 6. The derivative of cosine is minus sine times the derivative of the inside, so the derivative of 6t. And then for the next term, we have negative 18 times the derivative of sine times the derivative of 6t. So out front, we have a negative 36 sine 6t. The next term, a negative, positive, positive, that's negative. 6 times 18, I believe that's 108 cosine of 6t. So if we want to see, is this a solution to our differential equation, then we plug this in for the second derivative. So 3 times this plus 108 times y. So y is sine 6t plus 3 cosine 6t. And that should give us 0. So let's see if that's true. We're going to get negative 108 sine 6t. Distribute here, get minus 324 cosine 6t. Distribute here, we get 108 sine of 6t. Here, 324 cosine 6t. And if we look, The 108 sine 6t's cancel, the 324 cosine 6t's cancel, so we get 0 on both sides. So yes, that is a solution. This is a solution of that differential equation. And they don't come out and say this right here, but this is basically a mass spring oscillation. They and got all the derivatives on one side. They've let some of the constants be 0. So in ours, we don't have a y prime term, so our b is 0. They've got y's instead of x's, so our y prime's term doesn't exist, so that's 0. We have a y term, and theirs is an x. K is our coefficient of that, so K is 108, and 3 is our mass. This is acceleration, and we have no external force. So they just have it solved for the external force. Everything's moved to one side. But we don't have to necessarily know that. They're just wanting us to check, is that a solution to this particular differential equation? The other thing they ask for in this equation is to find the maximum of y. Find the maximum of y, which is just what is the peak, the farthest stretch that our spring has during this oscillation. So remember how we get maximums and minimums. We get critical points. That's when our first derivative is equal to 0. So our first derivative is 6 cosine 6t minus 18 sine of 6t. So that's our first derivative. If we set that equal to 0, then let's move the 18 sine 6t to one side. Typically, if we have two different trig functions, we want to factor. But since cosine and sine are different functions, we don't have a really good way to factor that. So what we can do is we remember that sine over cosine, hopefully, is tangent. So if we separate, then we can divide both sides by cosine, and that'll turn this into having one trig function. Instead of having sines and cosines, now we have tangent of 6t. So we can isolate tangent by dividing by 18. So if we divide both sides by 18, we would get a 1/3 on the right side. So to get what 6t needs to be, we can do inverse tangent of 1/3. And then when we get that answer, divided by 6. So that's going to tell us our critical point. That's the value of t for which we're at a maximum. That's not our maximum. That just tells us where our maximum occurs. So if we take that and put it in our calculator, we have 1/3. We're going to take inverse tangent of that, and then we're going to divide that by 6, and we get about 3.072. So they want to know, well, what is the stretch? What is the largest y value that we get? So to find that y value, we plug that in to our function, into our original function, sine 6t, 3 cosine 6t. So sine of 6 times our input plus 3 times cosine of 6 times our input. And then we just run that through our calculator, and that should give us what our maximum value is. So that 3.072, remember, it's going to get multiplied back by 6 before we take sine or cosine. So that's what's on the inside of sine and cosine. So I'm going to store that in a calculator. And I want to take sine of that. So that gives us our first term. We're going to add the result, so parentheses, of doing 3 times cosine of that number. So that number was 18 and some decimals. So we're going to take cosine of that, close parentheses, and we get our maximum y. It's about 3.16. 3.16. So after we got our critical point, which is where our first derivative equals 0, then we take that critical point, plug it back into our function to get the largest y value that we have. All right, so that's just a little preview from the first section of verifying that something is a solution to a second order differential equation. And even though in the problem they don't tell us, it's really a mass spring oscillation system that they're dealing with, and they're checking to see if this is a solution to that system. Now, as we get into 4.2, we're going to look at some differential equations more. So if we have kind of our standard form for a second order differential equation is this. And in this section, we're going to be looking specifically at when our second order differential equation is equal to 0. So we could have our function to the second derivative, our function of the first derivative, our function, and then we could have some function of our independent variable on the other side. But in this section, our independent variable is going to be 0. So we need to think about what will our solution resemble. Notice if we isolate our second derivative here, we would have minus by prime minus cy. So our second derivative is just a linear combination of our function and the first derivative. So you have to think what type of function would have a second derivative such that when we added the first derivative and the function together, those would be equal. That's probably not going to be something polynomial, because if we take something, let's say we suspect our solution is x to a power, then when we take our derivatives, our exponents get smaller and they get smaller. So notice this term, this 12x squared, is not going to be a linear combination of those two. If y is x to the fourth and the first derivative is x to the third, when we add those together, we're not going to get something in relation to x squared. So what our solution is going to look like, it's going to be in the form e to the at. Say y e to the at. Remember, when we take the derivative of e, the derivative of e to the x is just e to the x. So we're not changing degree or anything like that when we take the derivative of those. We're just replicating themselves. If we have some coefficient, let's say we have an a up there, then the derivative of that would be e to that power times the derivative of that exponent. So we still have that basic function for our first derivative, for our second derivative, for our function. We pick up a coefficient out front. So let's see if we can, let's look at an example. Let's suppose we have y double prime plus 3y prime, and let's do minus 10y equals 0. And let's suppose our solution is in the format e to the, and instead of calling it a, I'm going to say RT. So let's suppose our solution is of this format. Let's find out what R needs to be so that y is the solution of this differential equation. So if y is in that format, then y prime would be e to the rt times the derivative of the exponent. Well, t, when we say y is a function of t, so t is our independent variable. So this is a constant times our independent variable. So leave the constant alone. The derivative of t is 1. So y double prime is the derivative of that. So we already have an r out front. And the derivative of e to the rt is e to the rt times the derivative of the exponent. So we get r squared e to the rt. So when we substitute this into our differential equation, we get r squared e to the rt plus 3 times our first derivative, r e to the rt, minus 10 times our function, e to the rt equals 0. Notice all three terms have e to the rt. So if we factor out e to the rt, we have r squared plus 3r minus 10 equals 0. Notice the correlation between this equation and our original differential equation. We have the same coefficients that we had in our differential equation. In place of y double prime, we have r squared. In place of y prime, we have r, and in place of y, we don't have anything, just an understood 1. If we set this equal to 0, e to any power is never going to be 0. So that can't be 0. So the only thing that will make this equal to 0 is this part. So this is what we refer to as our characteristic equation. Our characteristic equation, or sometimes an auxiliary equation. This allows us to find the values of r that will make e to the rt a solution of that differential equation. And I'm not sure if I mentioned this earlier, but when we have the right side 0, remember the right side could be an entire function, but when it's 0, we call that homogeneous. Not homogeneous in the sense of what we talked about back in chapter 2 for homogeneous first order differential equations. This is a different type of homogeneous. But from here on out, when we have a differential equation that has a 0 on one side, we're going to refer to that as homogeneous. So if we solve this for r, we would factor it. Now, not every one of them will factor, so sometimes we have to use the quadratic formula. But if we factor, set each factor equal to 0, we would get r is -5 and r is 2. That means there are two solutions to this differential equation. R could be 2, so that would give us the solution e to the 2t. R could be -5, so that would give us the solution e to the -5t. So both of those should be solutions to that differential equation. So let's verify that. If we take the derivative of the first one, we would get 2e to the 2t. If we take the second derivative, we would get 4e to the 2t. And if we plug that into our differential equation, then we're going to have our second derivative plus 3 times our first derivative minus 10 times our function. And if we did that correctly, so notice we have 4e to the 2t here, 6e to the 2t here, minus 10e to the 2t. Well, 4 plus 6 is 10, minus 10. Yes, that's going to make 0. So this first one is a solution to our differential equation. Now let's check the other one. Our first derivative here is minus 5e to the minus 5t. Our second derivative is 25e to the minus 5t. So if we substitute that in, our plus 3 times our first derivative minus 10 times our function. And let's see if that. So we get 25 e to the negative 5t. 3 times the first derivative is minus 15 e to the negative 5t minus 10 times the function. 25 minus 15 minus 10 is 0, so that one also is a solution. So we have two different solutions here to our differential equation. And we started with just an arbitrary solution, a potential solution, and we found out what would R need to be so that it generates a solution to our differential equation. Not every value of R is going to work, but by solving our auxiliary or our characteristic equation, we found out which specific R's are going to make this a solution. So now let's talk about the relationship of solutions and what we can do with our solutions. So these were our two different solutions. So if we have an initial value, then how does that play into our solution? How does an initial value affect this solution? Because right now there's no arbitrary constant anywhere in here. T is our independent variable, Y is our dependent variable, but normally we have some constant, some C plus C times C or something in here that we find if we have an initial value. So let's see what would happen if we put an arbitrary constant in front of e to the 2t. If we take the derivative of that, that's going to be the derivative of e to the 2t is 2 e to the 2t, and we're multiplying that times our coefficient out front. Let's see, our second derivative would be 4c e to the 2t. So if we take that and plug in, that's our second derivative plus 3 times our first derivative minus 10 times our function, and that should equal 0. Notice each of these terms has got a common factor of c. So if we factor a c out, that gives us 4e to the 2t. 3 times 2 is 6e to the 2t minus 10e to the 2t. We've already seen that that's 0. So yeah, c can be anything. C is just any arbitrary value. So once we find a solution using our characteristic equation, then not only is that a solution, but c times that is a solution. So that allows us to find a solution specific to initial conditions. Well, let's look at what would happen if we added our solutions together. What if we added e to the 2t plus e to the negative 5t? Let's see if that's the solution. So our first derivative would be 2e to the 2t minus 5e to the minus 5t. Our second derivative would be 4e to the 2t plus 25e to the minus 5t. So if we substitute that in, we get our second derivative plus 3 times our first derivative. Remember, this is just the given differential equation minus 10 times our function. So if we distribute and collect like terms, we have 4e to the 2t, 6e to the 2t, minus 10e to the 2t. Notice that's 0. We have a 25e to the negative 5t, minus 10 e to the negative 5t minus 10 e to the negative, I'm sorry, this was 15 here. 3 times 5 minus 10 e to the minus 5t. 25 minus 15 minus 10, that's 0. So yeah, that's going to work also. So the general solution differential equation, if it's a second order differential equation in this format, homogeneous, then the general solution would be C times, for our specific one, e to the 2t plus e to the negative 5t with a constant. Well, it might be a different coefficient, so let's call this one C1 and that one C2. C1 and C2. So now let's look, generally speaking, if we have a y double prime plus b y prime plus c y equals 0, then of course our arbitrary or our characteristic equation would be ar squared plus br plus c equals 0. Whether that factors or we use a quadratic equation, notice we're going to get two solutions for this. This is a second degree, a quadratic equation, two solutions. So we're going to get an e to the RT with the first solution, e to the RT with the second solution, and each of those can have an arbitrary constant in front of them. So this is our general solution for second order differential equations, homogeneous. Now, as we progress through this, then we're going to find out that depending on what r comes out to be, sometimes we get imaginary values for r, sometimes we get radical values for r, sometimes r is repeated. So one thing that is mentioned in here is that these solutions, e to the r1t and e to the r2t, those need to be linearly independent functions. They need to be two different functions. And when I say linearly independent, essentially one does not need to be just a constant multiple of the other one. So what would be an example of something that is linearly dependent? If our first solution is 2e to the 5t, and our second solution is e to the 5t, those are linearly dependent because this one is just a multiple of the other one. So if we get the same r twice, then those are not independent, they are dependent. And we're going to find out how that affects our solution later on. So after glancing through, if we have distinct roots, this is the form. So this is for distinct roots. If R1 and R2 are the same, so if it's a repeated root, then our solution is going to be of the format C1 e to the RT. And to get one that is linearly independent from that, but still has that same R, we're going to multiply it times our independent variable. So these are linearly independent, even though they have the same power of R, or power of E, the same value of R. They are independent because the first one is not just a constant times the second one or vice versa. It actually has a variable times the second one. So these would be linearly independent. So let's work one or two more problems. Let's work y double prime plus 9y prime plus 6y equals 0. So let's solve this one. So our y is going to be in the format e to the rt. So our characteristic equation will be r squared plus 9r plus 6 equals 0. This one times r plus 3. If we set each of those equal to 0, we get a repeated root. So we can't have c1 e to the minus 3t, c2 e to the minus 3t, because those would be like terms. Once we add them together, we would just have one arbitrary constant in front of one term. So the way we said to make them linearly independent is we pick up a t in front of those. So this would be the solution to this one when we have repeated zeros. All right, let's do another one. Let's do y double prime plus, let's do 5y prime minus 2y. All right, so our characteristic equation is r squared plus 5r minus 2. And this one doesn't factor. So since it doesn't factor, we're going to have to use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So that gives us a minus 5 out front. Under the radical, we have 25 minus times positive times minus is positive. Two negatives make a positive, and that's going to give us 8. So we get 33 under the radical, 2 on bottom. So notice this is two solutions. This is negative 5 plus root 33 over 2. And this is negative 5 minus root 33 over 2. So our solution is going to be y equals c1 e to the negative 5 plus root 33 over 2 t plus c2 e to the negative 5 minus root 33 over 2 t. So regardless of how messy or simple our solutions are to our characteristic equation, we take those values of r, and that becomes e to the rt for each of those. So that's our general solution to our homogeneous differential equation. We don't get to solutions that have complex r values until the next section. In the second section, all of these are going to have real valued solutions to our characteristic equation. It's just going to be a matter of, are our solutions integers, are they rational, or do they have square roots making them irrational? And remember, if they're repeated, we have to pick up, we write it twice, but in front of one of them, we pick up our independent variable.